Good.
There we go. And I guess what we do is change the name, delete that, and change that name to that. So delete that one. Yeah.
Go faster. I hate steering this thing. Should have been Windows. Everything should have been Windows. And should Keith have this? Should we leave this here? Or
What's that? Where was it? Where do we say? Oh, we do full page, right?
Full mode.
Screen mode.
And we may have to go into preferences to tell it to cycle, but we'll see. 7 seconds. That works.
Nope.
Hey, good morning. Welcome to day 2 of OARC 27. Really just a few quick ones. Set up today is that we do the workshop until lunchtime. The public workshop then continues with lightning talks for just over an hour after lunch. Lunch will once again be downstairs in Club Regent Room. The other thing that we're doing during lunchtime is the PGP signing. Please get your keys to Matt at pgpsign@dnsoarc.net if you haven't already done, you want to participate in that. We'll probably use the Redwood room, which is just along the corridor for the PGP signing. Don't forget that Jerry is doing demonstrations of Drool and Check My DNS at the back of the room there, so if you didn't manage to catch him yesterday, please do that today. I think one or two of you had trouble with the surveys yesterday, but if you're having trouble, please go and speak to Dinesh at the registration desk and he'll help you out. But we'd really appreciate getting the feedback on the talks yesterday and today in the surveys. Really it just remains to once again thank our sponsors, ICANN, VeriSign, Thousand Eyes, Infoblox, and Comcast. And with that, I will hand you over to the session chair for this morning, Maurizio.
Good morning, everybody. We're going to start the track about testings and measurements. This is going to last until 11 a.m. So we welcome Paul Hoffman from ICANN talking about flexible testbed for recursive resolver software.
How do I make this go? I'm sorry? Escape. I would like to escape, but that didn't work very well. Sorry. Oh, and then now someone else is doing something. Is this guy doing it, or is that no? So let me preface this by saying ICANN does things other than rolling the KSK and not rolling the KSK. The slides you're going to see momentarily were turned in more than a week ago. So in it, you will see things that say, for example, October 11th. I didn't update the slides. I'm not seeing the slides. Yes, I would be happy to sit and talk about KSK more, which is sort of weird, but this is just because it's in my brain. But is this? Yes, that would be it. Cool. And now I'm in control with the arrows? Yeah. Great. Okay. So let me talk a little. I want to do an overview, partially because this is actually two test tools that I'm talking about at the same time. One is a resolver server testbed that allows you to run a whole bunch of resolvers one at a time with maybe different configurations, or you're hitting them with different queries, just to see what happens. And so some of this, I'll show you the main use case. Hint, hint, it was the KSK role. But then a second test tool that I'm going to be describing here is a test route creator. Many of us, in research over time have said, oh, I need to set up a fake route, or I need to do something for that. And we've all done it. I needed to do it. I said, oh, let me try to make this a little bit more general, and other people can use it as well. So the use case was, oh, look, there's that KSK word again. The use case was getting ready for the KSK rollover. I'll describe what the use case was sort of after I describe the tools. It still might be valid, but probably not. And then I'll talk a little bit about the next steps of what we can do with these tools. So I think a lot of the things this morning, people will be showing you tools and saying, hey, let's work with them together. And so my last couple slides are going to be on, it's actually sort of hard to make tools that other people use. We're really good at coding for ourselves. And I tried really hard in this. In fact, these tools are based on Python, and it's actually much more like validatable Python code than I normally would write, because I thought you all would be maybe looking at it, but still. So the resolver testbed, what I really want to do was, we said, well, what will happen when this version of bind, this specific version of bind comes up and we do this or that. So you want to launch a bunch of resolvers, not all at once, one at a time, with specific configurations, because one of the things we've discovered with the KSK rollover is you can actually configure your unbound or whatever in different ways, and it will give different telemetry. So in the testbed, I filled it with a bunch of open source resolvers. These are all running in VMs. This is what I've done so far, but you should be able to, in the testbed, also run proprietary boxes like Windows Server. Now, since I turned in the slides a little bit over a week ago, this last week was supposed to be me working on getting Windows Server working in it. So right now in this slide, I could say, oh, and I got Windows Server working in it. However, something else happened last week, and I've been busy. So we want the testing to not only be automated. Everyone says, ooh, automated. That's sort of like the cloud. But I wanted to be able to have it be flexible so that you could run a test just on all of the bind 9 ones, or just on all of the ones that do validation, right? Because there's a bunch of versions of bind that we don't do validation. So you should be able to tag each implementation to say which groups of tests it might be in. So bind, and of course you should be able to say all. The main reason I did this test bed this way is because we knew we were going to be looking at stuff. We wanted to see what does the resolver emit. So let's just watch it with TCP dump. And so we want to capture all of that, where really the data is not did it work, because pretty much resolvers will do something, but what did it do? And the best way to do that is to look at the TCP dump. And I wanted to have all of this work with the alternative routes, and you'll see why in a couple of slides, for this specific example that I'm doing. So no, I didn't really write any documentation. This is the best you're going to get for a man page on it. Basically, once you set up the test bed, and there is an install there, you say update all the sources, pull in all of the source code, compile it, make them all, and then build everything. And then each time you want to run a test, you say, resolver test. You get to make your own test name and the configs and such like that. So really, it's not like a huge, wonderful system, because I really think that the way that many of us work is we spend a lot of time thinking about what would we want these all to do. We design the test, we run it, and that's it. It's like a one-shot deal. So this is sort of designed around that way of working, which is I'm going to spend a lot of time preparing the test, I'm going to do it, and then I'm not going to keep running it over and over. So the config file for this, for putting together, is, it's JSON. But the first line there is the tags that you can put for each, each implementation. And this one's, that would fall in the bind 9. I also have a set of, I marked a bunch of them as recent. So we could, I could just run the test on the recent stuff. Oct stands for October, which of course now no longer stands for October. I will update that to some other month when I know what that is. The URL is where to grab it from. Base is, these are going to get built into VMs, and you could either, when you're setting this up, build a bunch of VMs, maybe one VM for bind and one VM for unbound, stuff like that. I ended up tossing them all into a common one. It turned out that that was just as fast. And then, of course, when you configure, when you are doing the configure during the build, not everyone says configure prefix equals whatever, you need some magic. So there's going to be a generic configure string, make string, and also how you start it up. So these are details, but basically that's the main part of the configuration file. So now let's go to the second tool that I did, which is the test route creator. So like I said, you've all done, or not all of you have done it, but many of you have done the, I need to make a route. I tried to make this generalizable enough. So for example, last night after the 6 o'clock session, someone came up to me and said, if the route just had this extra record in it, we could test and stuff like that. Some people were thinking that. And so this morning I got up thinking, I'll actually configure a test route that way. Unfortunately, the person sent me an email saying, never mind, that won't work. But the idea is that I wouldn't have to start all the steps again. I would be able to just nudge a few things and generate another new route. And the use case here was, what we wanted to test was a route that looked like, we wanted to run 2 tests. What does the route look like on October 10th? Which has 2 ZSKs and 2 KSKs, and what does the route look like on October 11th, which actually has 1 less ZSK. So instead of doing it and going, wait, but I need to do something different, I actually tried to automate that, and all of those things would be automatable. So, basically it takes a config file, puts out a directory full of files, including all the keys and such like that. It makes this is assuming that you're going to run bind as the authoritative for the route. So it makes the named.conf and all of that. But more importantly, it also puts out any of the files that you need for going back to the first part, going to the recursive stuff. You're going to want to spin up an unbound that is looking at this root server. So you're going to need a new root hints, and you're going to need, in this case, you're going to need new trust anchors. So it puts all of that out for you as you generate the root. Clearly, as this goes forwards and I have more things in the recursive part, it's going to spit out more. But the idea is once you say here's a root, you don't have to then go by hand and tweak all of the different recursives to look at it. You'll have nice pre-made configuration files for those as well. So the configuration file for doing this is not JSON. Oh well, don't call me consistent. But basically it says what are the IPv4 addresses that you're going to want in your root hints, what are the IPv6 addresses, how many KSKs are you going to want, And then you can do things like, oh, let's try it with different, kinds of keys. And one of the things that we're trying to model here, specifically for this, is since we wanted to see how big all of the priming queries would be, we needed to have it looking at something with the same number of letters as rootservers.net. So I made up a TLD and such like that. So you can change all of that in it. The last line is in fact, for October 11th, since what we were going to test was what happens if someone has just KSK 2010 on October 11th. So I needed to generate a trust anchor file that was wrong, that had the wrong KSK in it. So if I set wrong trust anchor equals true on this, it will actually generate bad trust anchor files, which is what I wanted for the testing. So it has things like that and easily extensible for that. So how many here think that we're rolling the root key on October 11th? No. Sort of the inverse of the question we've been asking for the last 2 years. So like I said, and again, I haven't updated these slides, so you can ignore the next bullet. What we wanted to do was to figure out, could we identify on October 11th who was priming and they had KSK 2010 only. So we thought, maybe if if we can see the queries going to the root, which we can because we have a bunch of root servers, doing to us, could we tell which implementation they had? That was the idea. So the goal was to get fingerprints where we could compare when they were doing everything right on October 10th and where they were doing things wrong on October 11th. So again, I created 2 roots that would look like each one. I created the test that would look like it, and then we looked at the PCAPs. So the bad news is we actually didn't learn very much. It was worth doing, but we actually didn't learn very much. We got all the fingerprints. I'm still going to do more because we have some more months now. And I'm going to be trying to add in more servers. But different versions of bind pretty much look exactly alike. We were hoping that maybe we could tell, oh, they're running 9.9 versus 9.10. Looking at all the TCP dumps of what we ran, that didn't turn out to be the case. We did determine that bind looks different than unbound, but all that's going to tell us is, maybe a little bit. And the power DNS recursor really didn't show us very much at all. So if we have widespread problems, maybe this will be a little bit useful, but it's much less useful than we had hoped it would be when I started doing the project. So here are the versions we tested, and I could easily add more in there. Now that I have more time, I will. These were simply the ones that are built in currently to in the config file. But as you could see from the config file here, it's trivial for me to add more, from this list. So we just figured this was a good representative sample of what we might see on October 11th. And you'll notice that not resolver is not listed here, and that's because it turns out, as we were doing this, we had been pulling down not, we've been talking to the folks at CZNIC. There was a bug in the way, just because they never thought anyone would want to be doing a different a different root hints and a different trust anchor at the same time. So I actually couldn't get it to come up and do it. So we didn't test any of that. I believe they've actually fixed that in the next version that maybe just came out or is about to come out. So we'll add that in as well. But we had actually were ready to test all of it. We couldn't get the configuration right. So let me briefly talk about what's next, which is, so we've done this testing, I'll keep doing more, but the one thing that many people here, or some people here have done, this kind of, oh, let's spin up a bunch of resolvers to see what they do, is how do they pick authoritative servers? So a lot of you have seen, in fact, I think at the last OARC was the presentation on recursives in the wild, great research. really interesting stuff looking actually out on the internet. We would like to reproduce that in a lab and try to match up. And we can do a lot more with that. We might also be able to reproduce what they're doing. Rarely in the DNS world do you get piece of research 1, piece of research 2 that then get rerun and correlated. Now, how do resolvers pick and change authoritative servers? Some of you might be saying, golly gosh, hasn't someone done that? Didn't they present that at OARC 5 years ago? And gee, Paul, wasn't that your boss? The bad news is they actually didn't keep a record of how they set that all up. So I'm going to be doing that from scratch. The good news is it's 5 years later and we can do a lot more interesting things with that. We can fudge with the timing much more easily. So any of you who care about priming and how do resolvers pick authoritative, please talk to me, because once we get the test set up going, it will be really easy to tweak things, to add things, to say, oh, but what if the name server it has this many letters in the name and such. So I would look forward to people doing that. There are also some things that come to the DNS OARC working group that, in fact, really are testable against recursives. It would be nice if this was available so that as things are getting to working group last call, we can actually try to shove it into some of these, if possible, and go to the working group and say, hey, look, we've got some data on that. So the other thing is anything that you all want. I mean, you can set it up, I can do it, but I'm interested. The last bit that I wanted to talk about is, okay, so I've been saying, ooh, you can do this as well. You always end up personalizing these things. So I would love collaboration, but if you want to fork this stuff, that's fine too. It's a really fine line between making the tool work for me and me trying to figure out how you would want to work the tool and what you would want and such like that. So I may have messed up. I think what we have in OARC is a long history of people doing tools, hoping that other people will use them, and really they end up being a single person tool with some great exceptions. And so this might be that. You might fork it, you might not. I tried to think of how other people would want to use this, but in doing that, and I was taking notes, I'm like, I don't know what everyone else is going to want. I didn't backtrack to just do it the way I want to, but that seems to be like a separate topic, is how do I write a tool that you might want to use as well. Last slide, please do use the tools. They're on GitHub. Pull requests, issues, whatever, that's great. Fork them if you want, such like that. I believe that there are a bunch of people who care about how do resolvers do things, what do they emit and such like that. If we can start sort of circulating around that and getting some more ideas, this might catch on, might not. This might be that I did this tool for this project, which was supposed to be done in 2 weeks, but oh no. And that's it, but I would like to see if other people have things that they want to do with that. So that's it. Questions? No, thank you.
Wes Hardiker, ISI. Awesome, Paul. I think that we've needed something like this for a long time, so thanks for putting it together. Have you looked at it?
You haven't looked at it yet, though, so you don't know if I put together what you wanted.
Correct. That's true, but I trust you. That's okay. Have you looked at putting in other things like DNS mask? I think would be the other common one to help pulling in. It is there now? No. I looked at it, and so as you notice, so I don't trust distros. I mean, I do trust distros. That's an unfortunate part of my life, is I have to trust distros. I don't trust them in this kind of testing because they make so many assumptions, both in their .configure, and after that they go, oh, well, I didn't like the way I did the .configure, so I'm going to mess it up this way or that. And in fact, going back to what's not happening on October 11th, one thing we've noticed is there's a bunch of distros that did interesting things with bind, where they said this will work, and in fact, one of the problems that has been discussed is some distros in the past made it so you couldn't write into your etc. named file, and so badness is happening. So I looked at DNS mask, and it's actually surprisingly hard to compile.
That's on my to-do list, but I actually put it after Windows Server.
No, that's fair. I mean, you know, the reason behind DNS Mask is it's in a lot of embedded, you know, kind of stuff. And that's the other thing we need to test.
However, in a lot of the embedded stuff, it has also been tweaked and such by the person. And I wasn't sure I was going to get any interesting information out of it. So yes, that, and yes, other things as well. You'll notice I don't have things like get DNS, you know, and Stubby on this, which even though Stubby is acting as a stub resolver, that would be useful to know how it emits and stuff like that. And it's not because I don't like get DNS. You know, I like get DNS. I helped get it going. But that's on the list. If other people want to throw things in, that's lovely. So, yeah, thanks.
Hi, Daniel Kahnberg. Again, yes, thank you very much. That's something, doing this in a reproducible way is really, really useful. So ICANN is useful. Oh, interesting. Anyway. As to what I want, I'd like to have your root servers have different performance characteristics, so that I can do the stuff that you mentioned about, you know, how do they pick and so on. So definitely that's, you know, high on my list.
Yep. So I don't have that in there now, but I certainly made it where, like, you can add a thing that says sleep for 50 milliseconds every time. You know?
Yeah. No, I might even help with that.
Great. That would be lovely.
The question, you know, has to be a question.
Yes.
What kind of loads do you use, and how? When I want to use a particular load based maybe on a real-life PCAP file, can I easily use that?
I'm sorry. What kind of loads?
Yeah. What kind of loads do you send to the resolvers?
At this point, just trivial. We were looking for fingerprints, not for responsiveness. Okay. I assume you can put any load on it because it's just running as a VM, you know.
Okay, so but you haven't got like a replay thing?
Haven't done anything with that yet.
Thank you.
But it sounds like you might.
Hi, Eric Zegas, Farsight. I think 1 or 2 ARCs ago, we set up a test lab for DNS TAP. Made it. I think Medica gave a presentation here about how that worked. There are so many variables beyond just the software, and I think it might be actually more important to test just, you know, real-world devices that are out there. Maybe set up a test lab as opposed to a test. I mean, test procedure makes a lot of sense, but maybe it might make sense for ICANN to run a test lab, just to say, hey, bring your boxes here. You know, you got your info blocks, your Microsoft, your, you know, it might be bind, but it could be Red Hat's version.
I've got
or
one.
Debian or
I actually have a lab set up to do that. And would be happy to have time to work on it. But I actually have a lab with, at this point, about 24 firewalls and routers and such like that. And as you said at the beginning, it's really hard to get good data out of them. There's so many variables. So I actually have sort of stepped away from it because it's so daunting. But let's talk about that, because I literally do have a lab that is exactly for that.
Cool.
Yeah.
Thank you.
Jimmy Tatia, Infoblocks. Yeah, this looks like a very good project. I like it. My question is, actually, before the question, so many interesting things with resolver can happen with more complicated scenario, especially involving delegation. So I'm wondering, how far are you planning to go in that sense, like making the configuration more complicated, or just focusing on a single scenario of exchanging?
That's actually an excellent question, because again, I started it with the one goal in mind, and I was hoping that I would come and give a talk here and other people would go, oh, that's cool. So I tried to make it generalizable enough. The hardest part is configuration, right? Bind configuration looks different than unbound configuration, such like that. So that's a weak part, but I did try to leave as many variables in there as I could. The nice thing is this is all Python. It can, you know, you can always add another layer of indirection on any of this. And so if you have a specific thing you want to be doing in that, even if it's different than what everyone else is, I'm still happy to put that in for you, because the next you afterwards is going to say, oh, look, I can do it this way. So I'm happy to do things like that.
Okay, hopefully I can contribute to it.
Yeah, great, thank you.
Hi, Jim Belton, OpenDNS. Quick question, how do you test your software that you've developed? So if I were to go in and make changes, how do I verify that I haven't broken anything that's there already?
You're asking, like, did I write test cases in my
Yeah.
software and such? No, of course not. I'm a normal person. I don't know, and that's an interesting question. I sort of pictured that people would put in change, pull requests and such that would be chunkable, and I'd look at them and everything would be okay. And if this gets too popular, I'm going to have to do unit tests.
Yeah, PyTest is really good for that.
Okay, great. Great, yeah. No, but no, seriously, I didn't. Yeah. And as I was developing, of course, did I have unit tests? No, I had print statements. So, yeah. I'm a normal person that way. Yeah.
Yeah, I guess I'm not.
Yeah. Great. Thank you.
Thank you very much, Paul. Now we have Mr. Daniel Karenberg from the RIPE NCC.
Yeah. And if you can give me my browser back. Yeah, it's in the browser. So you just deleted that window? Oh, okay. Yeah, I need the... I set up a nice window with the schedule for today. Adjust the schedule for today. Will be fine. Yeah, I'll take it from there. Don't worry. Yeah, there we are. No, of course it doesn't. It's on the right, okay. No? Okay, here we go. Apologies, everyone. This actually dovetails quite well with the previous talk, because what I did is I looked at priming queries in the wild. And to give you fair warning, this is a half slot, so it's only 15 minutes. And I promise to make up for it in entertainment value and surprises, and there will even be a soapbox at the end. So if you can just stop reading your email for 15 minutes, you'll be entertained. How did I get to this? Well, basically, I looked at the DSC statistics that we publish, and that's even available at OARC, about the most popular queries at the K-root name server. And to my great surprise, the priming queries, the ones for dot and S, are the third most popular. And that's really surprising, because it's a really boring query, and people shouldn't be doing it that often. It's just before all the junk like local and home and all that stuff, which isn't even delegated. So that was what sort of made me curious. And so I'll do a very short refresher on priming queries. This is OARC, you should all know this. This is the priming query. The answer is the most boring that there is in the DNS. It hasn't changed for more than 20 years. The root servers are A through M root. Well, big surprise. Of course, the purpose is all about the additional section, the glue, the service addresses of all those root name servers, and even that is pretty boring. It doesn't change very often. I think it hasn't changed for a year or so, and the next thing that's coming up is a change in one address in there for B. So that's also very boring. Let me just go through this. And then we did a lot of work on the additional section in case the UDP size is only 512 bytes. So if it's a really old kind of server or resolver, it doesn't get the whole list. I mean, it used to get the whole list, A through M, but then we went to IPv6, and now it doesn't even get the whole answer. So in the future, where we have fully migrated to IPv6, even then, it wouldn't, the additional section for those poor resolvers that can only do 512 bytes will only go A through J, and K will be out of business. But you all know this, so I'll just carry on. So this is what basically started me getting curious, and I did the proverbial back of the envelope calculation and basically said, if it's 2,000 queries a second, how many well-behaved resolvers could we actually serve that way? Remember, the TTL there is 6 days. So if you go and multiply 2,000 by seconds, by minutes, by hours, by 6, you get to an interesting number. Does anybody spot what's weird about this? Well, it's the front of the envelope. It's not the back of the envelope, and I can do this because these envelopes are basically scrap paper. We changed our logo. But what's really... oh, people are listening. So what's really weird is the bottom line there. The bottom line is like more than 1 billion. And who in the room believes that there's more than 1 billion resolvers out there in the internet? Thank you, George. Anyway, and of course everybody will now say, or the people who are still with me will say, well, nobody believes TTLs of more than a day these days. So then I have to divide this by 6, and still it's like 175 million, and I don't think that's even realistic. So that turns curiosity into research. And of course, it's a work in progress. I thought I had much more to say today, but still interesting stuff. And there's more to come. And if you have suggestions, they're very welcome. You're very welcome. So what do you do with research? First thing you do with research is get data. So I got data and I cleaned it, which is usually half the work here. I got data for 7 days. It's just 1 day more than the TTL, and it's like also a week. So that was quite nice. And the interesting thing here is the bottom line: 1.2 billion. 1.2 to the 10th to the 9th is the number of queries I got. That's a bit more than the back of the envelope because it's 7 days and not 6 days. And if I divide it by the number of seconds in that period, I come out at 1,972, which jibes pretty nicely with the 2,000 per second that DSC says. So I'm quite confident that actually I've not done anything really strange in doing my data cleaning and so on. So then there's a bit of statistics, 17.7% IPv6, 95% DNSSEC OK, 95% UDP, and surprisingly, more eDNS extensions than UDP queries. So people are doing eDNS over TCP. If somebody can explain this to me later on over a beverage, I'll be interested. But interesting again here is the bottom line. The bottom line is we only see about 4 million unique source addresses, and I'm quite aware that unique source address doesn't mean client these days, with NATs and all that kind of stuff, but it's the ballpark. So here we are, a couple of order of magnitudes less clients than we would support if they were all well behaved. Now, actually looking at this, I have to move out because the screen's not big enough. This is actually one of the central graphs here, and what I did is I basically looked at the number of queries we receive from the each unique source address, and I normalized it down to a query per day. So you have days on the x-axis, and mind you, the x-axis is logarithmic. And it's a CDF, a cumulative distribution function. So what the dot that has the blue arrow actually tells us is that 1 query a day, a little bit more than 60% of all clients query us once a day or less. Yeah. And you can actually count the dots down there, and you see that that it's like 25 and a bit % of all the queries we only see, of all the addresses only query us once in those 7 days. But the really astounding thing is what happens in the red area. The red area, I just basically said everybody who queries us on average more than once an hour is probably hyperactive. And especially the guy up in the right-hand corner is totally hyperactive. So what to take away from this is that only just over 60% of the clients are well-behaved, in my definition, so less than or equal to once a day on average. And 10% of the clients, that's where the black line hits the red area is 90%, right? 10% of the clients are actually hyperactive. They query us more than once an hour on average. And how hyperactive they are, you actually see if you make the x-axis linear rather than logarithmic. And you see a very interesting CDF here, which is basically a square wave with dots really up and on the right. So I could not help myself but actually contact the organization that did the queries on the top right. I mean, there's more than 400,000 a day, and that translates to more than 5 a second. Yeah. So here's the conversation that ensued. I basically, I happen to speak their language, so I go like, morning, I can't help but asking, what's happening there? Are you under attack? Is this a reflection thing? And I was quite sure it wasn't, because they all came in on one instance. So at first they went to, we'll look into this, and then they went like, oops, no, that was us. We really sent those queries, and we fixed it. Thank you. So I couldn't help but ask, how did you do this? I mean, what happened? And they just said, we configured Unbound basically to turn off the cache. You can do that in the Unbound configuration, basically the way it's shown here. And then I said, why on earth did you do that? And they said, well, we really wanted uncached answers, so we turned off the cache. Yeah. And that left me speechless, and that doesn't happen very often. But what really happened there is, I'm quite sure, is that there's computer scientists, and they say we want uncached answers, so we turn off the cache. I mean, they didn't understand DNS really, and they're sort of in a DNS-related business. So what we have to understand is that people who are using this stuff, sometimes quite intelligent people and so on, they just don't understand the intricacies of the protocols and of the DNS system. So my takeaways here is, of course, in DNS there's always another surprise, especially in operations, and DNS software should have safeties. I mean, you don't construct weapons without safeties. DNS software should really have safeties. So I know that the Ananda Labs folks are here. You might want to consider actually making it not run and barf if somebody configures it like that. And they should at least have to recompile it to do stuff like that. My opinion. Okay, looking at the load, and this is the same graph, but now the y-axis is the number of queries, not the number of unique clients. We see that the well-behaved ones, at the blue arrow, are basically not registering. They're about 1%, or even less than 1% of the queries are actually coming from the ones that I defined as well-behaved. And if we look at the hyperactives, 95% of the queries come from the hyperactives. Yeah. And that doesn't surprise me in general on the load on the root name servers, but for the priming queries, it was kind of surprising because I thought, that's so special, we shouldn't be seeing stuff like that. And then I looked basically at the how long they're at it, and if I take only the hyperactives and just look at, when do I first observe a query from them and when do I last observe a query for them in those 7 days, and subtract one from the other, I actually see that from the hyperactives, most of them actually keep at it. They're there during all the 7 days. I mean, they never stop. That makes me sort of think it's probably not like, spiky attacks or something like that. They just keep at it. They keep doing it. And if we look at, on the contrary, on the well-behaved ones, the ones that only query us once a day or less, we see that we only see them once, and then there's a couple of peaks around periods of days, and that makes me think, yeah, that's probably like max TTL and stuff like that. I'm done. So the takeaways here are, as somebody else has said, almost all queries to the root name servers are not useful for DNS resolution. Yeah. And now we found that even holds for priming queries. The well-behaved are less than 1% of the load, or about 1%, and the probably not useful are 95% of the load. And we should ask ourselves, is this good engineering? Because it's very easy to point the finger and say, hey, those are the clients, and we're not responsible for the clients. But I think we as a group should feel responsible for the system as a whole. And if we have a system that has this kind of stuff in it, then probably it's not good engineering, at least my opinion. And then the last bit that I have here is about the distribution of the eDNS sizes, or actually it's a misnomer here, the distribution of the accepted response sizes. You can read that from the right. So the good news is that more than 50% of all the clients actually accept 4K responses, and about 2/3 accept something like 1472. And only about 1/3 actually either don't have eDNS or give us eDNS and say, hey, only 512, please. So the takeaway from that is that bigger responses are acceptable than back in 1995 when we basically did this naming scheme, the rationale of which was, let's only have A through K because then the additional section is less than 512. So probably we could add a few more root servers. And there's a bit of further work. If you want to help with it, you're welcome. I'll probably chug along next to my day job doing some of this stuff. And here's the promised soapbox. The question here is, should we add more addresses or root name server operators just because we can? I'm not quite sure. There's political reasons, but I don't see any engineering reasons to do this. But we have to face it that people are catching on to the fact that there's eDNS and that our defense of limiting the number of root name servers to, or service addresses to 13 is probably not valid anymore, or as much as it was. Distributing and caching the root zone more aggressively, and I saw some of this discussed yesterday. It's very encouraging. I think that should happen. We should move away from root name server system and root servers that have to take all possible abuse and be assistance in distributed reflection attacks and stuff like that. And also, we should move away from sort of root name servers that are really sort of in a special, unique position in the internet. That's not the internet way. We should move to a more distributed system. And then my appeal to this community, especially the people who engineer the software and the protocols, to me it seems like the root zone is a 2 megabyte file. It changes once or twice a day, and the changes are very localized and minimal. Some days it doesn't change at all. There must be better ways to distribute this file. I mean, it's like just because it's a DNS zone file, it doesn't mean we have to distribute it using the DNS protocol. Maybe we can think of better ways of doing this. And I'm done.
Okay, we have short time, 2 minutes for questions.
Hi, Daniel. Wes Hardiker, ISI. Did you check to see whether your data aligned really well with sort of what was in RSEC 003, I believe, where it was determined that a good percentage of the software out there queried for the root NS records once an hour, I think. It was like a 50% line, right about once an hour.
No, it's not 50%. I mean, the question was basically, is the load spiky on the hour? So what I see is the load is a little bit spiky. Unfortunately, I don't have the graph right here, but I can add it to the materials. It's a bit spiky on the hour, every hour on the hour. But that's about, I think the spikes sort of from just looking at it are like 5% above the normal level. That's what I'm seeing there for the priming queries. And that tells me that people basically reload their resolvers or restart their resolvers on the hour, dotty on the hour. Maybe they shouldn't do that, but it's not a big deal. Does that answer the question? Okay.
Just we're closing the ears.
Eric Zigas, Farsight. When you say there are things that we should not do, when you use the word should, that starts to sound like an RFC, and I'm wondering maybe name servers would be RFC something compliant of here are some things you should not do to help the roots and the system in general. And maybe that's a way to progress from here.
Okay. Any volunteers writing that? Thank you.
Thank you very much. Now we have from the Japan Registry Services, Mr. Kazunori Fujiwara.
Hello, I'm Kazunori Fujiwara from JPRS. Today, I will talk about cache effect of shared DNS resolver. It is a joint research with University of Tsukuba and JPRS. This material comes from proceedings of CompSAC 2017, IEEE Computer Society Signature Conference on Computers, Software and Application. This is today's outline. Related works, issues and evaluation, DNS traffic data at University of Tsukuba, analysis results, a number of DNS queries to authoritative DNS servers and application ratio, and frequent queries and active clients, and then conclusion. These are related works. In 2002, Jian et al. Reported on DNS performance and the effectiveness of caching. They collected many data and evaluated the effectiveness of caching. And 2012, Fujiwara et al. Reported DNS traffic analysis issues of IP version 6 and CDN. It analyzed a shared resolver. It analyzed one of the shared resolvers in an university, and the main results are that average cache hit rate was 75.1%, and a client query generates 0.00079 root DNS server queries and 0.025 TLD DNS server queries and 0.28 other DNS server queries on average. And then in 2014, Shkomp et al. Reported DNS resolvers considered harmful and proposed removal of shared DNS resolvers and use of full service resolvers at the end clients instead. Then a paper proposed removal of shared DNS resolvers. However, removal of shared cache increases DNS traffic. So we need to evaluate effect of local cache and shared cache. To estimate cache effects, we performed minimal resolver behavior simulation with real queries from clients. So we captured at one of busy resolvers at the University of Tsukuba. And this is our data collection system. Academic Computing and Communication Center offers full service resolvers for campus network with the university, and we captured DNS traffic at the full service resolver. Capturing date is 2016 December 1, 24 hours. And the capturing point is full service resolver of campus network, and the number of clients is 6,475. Number of query names is 290,000. Average number of queries per minute is 14,244 queries per second average. And these are our resolver simulation details. We made an assumption. Authoritative servers are 3-layered root TLD organization as a second level, except in JP domain name. And each query counts up number of queries counters for root TLD organization. And we considered 3 cache scenarios. Number 1, without cache. All queries from clients generates queries to root TLD organization, DNS servers. And number 2, with local cache. We performed cache simulation in each address. Number 3, with shared resolver. We performed cache simulation with all queries. And there are many limitations of our simulation. We ignored CNAME chain following, out-of-basic name server name resolution, and domain name existence. And TTL at organization second or third level is 300. And our evaluation is very short term, 1 day only. So this is preliminary result. And the figure compares the estimated number of DNS queries sent out from the network to authoritative DNS servers. And the assumption of organization TTL is 300. Horizontal axis is time in a day, and vertical axis is number of queries to authoritative DNS servers in 5 minutes. Without cache line is about 170 to 600, and with local cache line is about 50 to 160 query per second, and with shared cache line is about 20 to 40. Without cache line is similar to number of client queries. The graph shows that local cache and shared cache decreases queries to authoritative DNS servers. And the next graph shows amplification ratio of authoritative server queries. Horizontal axis is time in a day, and vertical axis is amplification ratio. Plus shows number of queries to authoritative DNS servers without cache divided by number of queries to authoritative servers with shared cache. And dot line shows with local cache divided by with shared cache. On average, the case without the cache amplifies the DNS traffic 12.1 times. And the case with local cache amplifies the DNS traffic 3.3 times. So removing shared resolver will amplify DNS queries to authoritative DNS servers 3.3 times. And next graph shows query amplification ratio per TTL. Horizontal axis is cache TTL value, and vertical axis is amplification ratio. This graph shows longer TTL result in larger amplification ratio. Even if very short TTL 60, amplification ratio is 2.6 times. Next graph shows number of DNS queries for TLD DNS servers and second level DNS servers. Horizontal axis is time in a day, and vertical axis is number of queries to each authoritative DNS servers in 5 minutes. The number of queries to organization DNS server is larger than number of queries to TLD DNS servers with the local cache and with shared cache. This shows that the caching mechanism is more effective for TLD than for organization DNS servers. Next graph shows amplification ratio for second level DNS servers. Vertical axis is amplification ratio. This graph shows shared cache decreases second level queries are little. Second level domain DNS servers are little. 20% of no cache scenario and 40% of local cache scenario. Next graph shows query amplification ratio for TLD DNS servers. This graph shows shared cache decreases TLD queries well. A 20th of no cache scenario and a 5th of local cache scenario. And next graph shows query amplification ratio for root DNS servers. This graph shows shared cache decreases root queries well. At 10,000th of no cache scenario and at 10.9th of local cache scenario. So removing shared cache is harmful for root DNS servers. And during the experiments, we found a few clients repeatedly issue many of the same DNS queries in a short interval, and also a few queue names are repeatedly issued in a short interval. Next graph shows frequent query names. Horizontal axis is query interval, average query interval in second, and left vertical axis is cumulative number of query names, and right vertical axis is cumulative number of queries. This graph shows 4.3% of query names are sent within an average interval of less than or equal to 60 seconds. The total number of these queries is 71.7%. Very small number of query names constitute of 71.7% of queries. And next graph shows frequent clients. Horizontal axis is query interval, average query interval in second, and left vertical axis is cumulative number of clients' IP address. And right vertical axis is cumulative number of queries. This graph shows that 64.4% of clients issue DNS queries with average interval less than or equal to 60 seconds. The total number of DNS queries from these clients constitute 94.5% of all client queries. Very high ratio. And next graph shows most active clients. Most active clients send 2.1 query per second average, and very small number of query names. The client doesn't have, or the client uses shared cache as a local cache. And these are our conclusion. Removal of shared resolver replaced with local resolver can be expected to amplify the DNS traffic by about 3.3 times. The amplification ratio on the root DNS server is much worse, about 10.9 times. So removal of shared resolver may be harmful for root DNS servers. And some systems, Linux BSD, lack local cache. They generate repeated queries at short intervals, less than 1 minute. And they are about 94.5% of all client queries. The deployment of local cache itself is effective for shared cache. So, and there are many our future works. We would like to perform long-term analysis and comparison with real traffic, because real queries from full service resolver to authoritative servers are recorded in PCAP file. and we would like to perform detailed full resolver simulation, and we would like to analyze new DNS standards that improve name resolution performance. RFC 8020 NX domain and RFC 8198 aggressive use of DNSSEC abbreviated cache. These new proposals will decrease queries to authoritative DNS servers. Then the result, this result may be changed, I think. That's all.
Wes Herdeker, ISI, thanks for doing this. I have been wondering what the amplification would be like if say, every laptop became its own caching resolver without a shared. And so this is wonderful starting data for that. Thank you.
Thank you.
Ralph Weber, Nominum. So I have two questions. So the first one, I wasn't totally clear on your experiment. Did you sort of set up a fake root and TLD server, or did you send the queries out to the internet?
Currently, we analyzed client query names only. So we counted query name pattern only. So currently, we didn't send queries to the internet.
Okay, and my understanding, okay, so you took the PCAP that you have and analyzed it, that's right?
Yes.
Okay, good. The second question, you had on the slide, the servers was doing around 200 something QPS in total, and I'm not sure, did you have the cache hit rate up there for this QPS?
Pardon?
The server that you investigated had 200 QPS average query load, and I was wondering if you had the cache hit rate for that server, how often something was served out of the cache or not?
Currently, we don't calculate cache hit rate, but it may be the same, about, I think, 75%.
Okay, thanks.
Petr Špaček, CZNIC. Nice work, thank you for that. And to the future work, I have a note about 8020. Our experience is that it breaks stuff. So if you are going to do some simulations with RFC 8020, it usually breaks stuff. So for the practical purposes, we limit that to DNSSEC signed domains only. So I would recommend you to do the same in your simulations or future work. Otherwise, you will be not simulating real behavior on the resolvers. And one other note, it might be really interesting to see what's the impact on the latency, because I haven't seen any numbers about latency, but if you are talking about a case where you replace all the shared caches with the local resolver, I would strongly recommend you to measure latency for the client, because that might be the breaking point where people decide to do it or not. Thanks.
Thank you.
Jim Mate at the InfoBlocks. Could you go back to the slide talking about the BSD and Linux? A couple of slides before, I think. No. It's just only a Barrett, and not this one. You are talking about the resolver of BSD and Linux and saying that it doesn't cache or something like that. Oh, yeah. So I guess you are referring to the standard libc kind of library here, right?
For example, Windows or Mac OS uses local cache. And BSD or, for example, FreeBSD case, FreeBSD use, we can use Unbound as a local cache. So I don't think the local cache is implemented in libc.
No. My question is specifically which resolver are you referring to here? I thought you are in this part. I think you are saying that the libc library of BSD and Linux lacks local cache.
Oh.
No, that's true, but I'm trying to confirm that.
Currently, I don't say implementation method.
Okay. Yeah. Anyway, my main point here is that it's true that the standard libc library of Linux or BSD lacks local cache, but it also doesn't even do any the full service recursion. So this in that case, this comparison doesn't make much sense to me. That's my point. Maybe we can talk about. But anyway, that's a minor issue. And actually, another related point is that I guess in this comparison, considering the behavior without cache doesn't make much sense probably, because DNS highly relies on the caching anyway. So if we want to research into the effect of not sharing the cache, the interesting comparison will be comparing the shared caching and local caching.
Yes.
So including this comparison, including the comparison of the shared caching and no caching may be interesting, but that seems to be a minor issue. So probably more focused if you concentrate on the comparison between the shared cache and local cache.
Yes.
Hi, Daniel Kahnberg, RIPE NCEC. I just wanted to make sure that very nice work, but even if you look at the second bullet point there, that you have an amplification ratio for the root name servers of about 11 times, people should not in their mind translate that into an increase of the load on the root name servers by a factor or by an order of magnitude, because we've shown a couple of times, and even in the previous talk, that the useful load on the root name servers is like very, very low compared to the unuseful load. So it's not like, if people do this, even if everybody did this, the root name servers would probably not notice it.
Thank you.
Thank you very much. Next we have Mr. Geoff Houston from APNIC talking about DNS over IPv6.
I have 15 minutes, right? Cool. 20. I'll go a tiny bit slower. This is actually about UDP and IPv6, and it kind of follows on from a talk yesterday, I think, by Stephen Lagerholm about this same topic, but I'm looking at it from an entirely different perspective. And what I'm trying to understand is actually the fate of large DNS responses. In other words, what happens, for example, in DNSSEC when you actually pack multiple RRSIGs into the answer. Here is .org, dig.org with the DNS key resource record with DNSSEC enabled. You're going to get back a response of 1,625 octets unless you're on T-Mobile. Even now, today, when you do a dig of the DNS key resource record in the root domain, you will get back 1,414 octets. And 1,425 if A, the roll ever proceeds, and B, we get to actually revoking the old key. So big responses are actually part and parcel of the DNS today. So what's going on here, and how does the DNS handle big responses? Well, a long time ago, before eDNS 0, and even today, if you don't have eDNS 0, the authoritative server, when it gets these requests, is meant to say no response is greater than 512 octets. If I'm going to try and give you a response larger than that, I'm going to stop and set the truncate bit. So the truncate bit had a special interpretation. The idea was if you can't get it in UDP, you're meant to try using TCP, off you go. So basically what they're saying is, if I offer you a large ENS 0 buffer size in UDP, then you can send me one. Now there's a really big assumption going on there that I might as well make explicit right now. On the network path between me, the server, and you, the client, if you say I can offer I can handle a really big response, I, the server, say, you're speaking about the network as well as yourself. Wrong. But let's understand why that's wrong, because the implicit assumption on EDNS 0 is that you and your network path are the same. There are other bits about UDP fragmentation. If we weren't here in OARC, but we were here in some kind of network security conference and I said fragmentation, you would hurl rocks and rotting vegetables at me because obviously fragmentation is evil, it's a security risk and should never, ever happen. And a whole bunch of firewalls implement that practice even today. So fragmented UDP doesn't work everywhere. In V6, we cluttered the network with tunnels because, tunneling's fun and everyone should do it, not. And what happens then is, of course, the tunnels implicitly alter the path MTU. My MTU and your MTU is not the same as the network MTU. Oops, the packet kind of dies in progress. Now, in V6, that's a very special kind of die because routers aren't allowed to fragment packets. So when the packet is too big for the next hop, V6 goes gack and simply barfs the packet into the great bit bucket in the sky and takes a small amount of residual nonsense and sends it backwards using ICMP. Remember what I said about that security conference and fragments being really evil and we should drop them? ICMP packets are unauthenticated noise from the middle of the network and anyone can generate them. So if you're a security person and you really worry about this kind of stuff, ICMP packets are just as evil. And so a lot of people filter them no matter what. Even ICMP packet too big packets, which is really a problem if you happen to be running UDP. So you might not get the packet. And even if you're running UDP not TCP, and someone sends a message saying, hey, that last datagram you sent didn't make it, so what? I haven't kept a copy. I have no memory. I'm UDP. So what am I going to do with that advice? Helpful as it might have been. It's not going to cause retransmission. That's a problem. Last and not least, if you thought this was really easy, we decided in V6 that we weren't going to put fragmentation control in the header because after all, fragmentation is indeed implicitly evil. So therefore, just to signal the fact that it's so damn evil, we're going to make a special packet and make the packet longer, and we're going to make this an extension header. And if you've ever read RFC 7872, which tested the Alexa top, N servers, and sent those servers extension headed packets, an incredibly large number of them just didn't like it. They just discarded it. So it seems that's a bad idea. And a lot of folk agree with the fact that's a bad idea. I'm asking Google, using a rather special domain that only answers in V6, a question where the response is more than 1,500 octets. I don't get an answer. Thank you, Google. I really appreciate this. Not. Well done, thank you. So this is in many places, including folk who I thought knew better than this, that somehow big answers in V6 are an invention of the devil and cannot be supported. So what happens? Well, you guys just drop it on the floor because, you just don't handle V6 fragmentation. Okay, so let's all use TCP. Yeah, right. I gave a talk, it was back in October 13, looking at precisely how many folk block TCP and DNS, and it's non-negligible. Around 17% of resolvers at the time said that TCP over DNS was indeed not worth passing through, and they dropped it. This affected 6% of users. You go, oh, well, they'll go and use another resolver. Not quite. At least 1 in 50 users had no choice. So if you say TCP works, you're kind of going, well, except when it doesn't, which isn't really the right answer either. How am I going on time? Still getting there. So, TCP won't necessarily help you between a rock and a hard place. Because the other thing about dropping UDP is there's no truncation signal anymore. When you send a query, you don't get back a signal to use TCP, you get nothing. Absolutely nothing. What are you meant to do with that? So you're just going to repeat the query. You're going to get nothing. Now what? So this kind of unresponsive behavior doesn't mean query you're using TCP. It simply means, wow, go and use eDNS 0 combinations to go and find something that might work. This is bizarre and broken. How broken? Well, the problem here is actually a problem about v6. Because in v4, with forward fragmentation, frags normally got there. And unless you were kind of, oh, well, I'm going to put frag filters up in front of my DNS resolver, things kind of work, including .org. If we ever had a v6 only world, things would kind of not work and you're kind of stuffed. So I put up an ad platform and decided that I would give folk really, really big answers in v6 only. We ran using a relatively small MTU, so it trapped folk into actually getting fragmented v6. And the first thing is, you know, hey, there's a lot of v6 out there. There might be only sort of 20% of end users who can actually use end-to-end v6, but out there in DNS resolution world, about half of you, almost 3.5 billion, can use v6 only resolvers. I'm going to keep on talking and use up all the question time. Stuff it. What's the result rate? Pretty bad. About 42% of folk didn't work. But notice that 7%, even with a small packet, it wasn't working properly. So while I found some differences, the experimentation technique really doesn't work very well. Because this is difficult, because a silent drop doesn't really tell you much. And if you're trying to equate DNS resolution to fetching a web object, you're really in a very, very bad place. Roll back a few years ago when there was a really good presentation about using a DDoS attack with glueless delegation in the DNS. We can use this. Because glueless delegation forces a resolver to take a query about the actual addresses of a name server and then resume the main query. If I twiddle with the response coming in on figuring out what the name servers is, I can trap the resolver into signaling me directly whether it received the answer. So you start going down the normal resolution chain, you send an answer saying, here's some NS records but no address. Go figure it out yourself. It has to stall one, go and figure out what the address was and then resume. So what if the answer from the glueless delegation part was really, really, really big? Oops. Someone's got to figure out how to do really big v6 packets and we can measure them. Unfortunately, you guys who do DNS resolution software got there before me, and instead of using eDNS 0, you send me queries using no options at all. Bugger. Because now I'm going to send you a truncated answer, the whole thing fails, I'm not there anymore. Okay, part 2. If you won't let me send you a big answer, I'm going to send you a fragmented answer even under 512 because, you know, it's a computer and I can do that. So I start sending you fragmented small answers just to see at the IP level if you can reassemble this shit. Wow. 38% of folk, and there were 10 million of these tests that I did, 38% do not like a fragmented answer, including Google's public DNS. There's the failure rate. We saw 10,000 discrete resolvers, 3,500 just really, really didn't want to do it. Who are they? Well, if you're on this list, you can't do it. Individual addresses and places. I don't think many of you are in this room, that's fine. What about Origin AS? Well, some of you are in this room, thank you, Google. Thank you, Cellco, Verizon. If you see yourself here, you've got trouble. I've got 2 minutes left, there really won't be any questions. So what's the problem? You don't like extension headers. So if you don't like extension headers, let's go and change v6. Yeah, right, let's make the pigs work, yeah? Never going to happen. Let's alter the way v6 fragments. Let's strap rocket engines to the pigs. It's still not going to work very well. Or, you know, let's move the DNS off UDP and see if TCP works. You're equally just totally fried. We are really, really in a bad place here. The end answer is you are so addicted to v4 in the DNS, you're stuck here. Totally stuck. We can't move it to v6 because the installed base is so crappy about extension headers, that's not going to work. You can't constrain the bloat pressure in DNS, can you? Because you're going to, I saw someone doing multiple RR sigs when we roll keys, etc., etc. So that's not going to work. Changing the entire carriage protocol of the DNS, yeah, right, keep me laughing. So seriously, No one is motivated to fix this problem while v4 exists. Anyone in this room. Because, quite frankly, you don't see it, not even the operators of .org. Because v4 exists, no matter what crap you do in the DNS, v4 is just going to fix you. So why fix it? So you don't. So if anyone even vaguely thinks that there is a die time for v4 completely, when the DNS has no recourse to v4, at that point, when you're falling off the cliff, when you're entering the free fall of gravity, will you then figure out, oh shit, yeah, I should have fixed that fragmentation problem with extension headers? Too late. At that point, this appallingly bad drop rate, 38% of all these folk who are using these v6 capable resolvers cannot figure out what to do with responses in v6 that include extension headers. So what do? Change the protocol behavior? No time, no motivation. It's just an academic exercise and more kind of stuffing around. Change the way in which we respond by explicitly including truncation signals when we fragment. Davey Song had a neat idea with adding a truncated response record, trailing behind fragmented UDP. If you don't like these fragments, here's something that says use TCP. Interesting idea. It turns all queries into amplification factors. Or we can change the transport. You've seen that as well. So where do I end? A lot of folk helped me to do this, including Ray Bellis down the front here. We basically re-engineered the DNS to make queries a microcode program and make the DNS server a microcode engine. So that basically by sending the right kind of queries, you can generate the right kind of responses, anything you like. And by putting it inside a glueless delegation, you can actually trap the behavior inside the DNS and get the DNS and the resolvers doing this to report back to you on how well they're doing without relying on anything else. The end result, if you really think a v6-only future is in your line, I don't understand the drugs you're on, and I wish I was on them too. Thank you very much.
So we have 5 minutes for questions.
Do we? I would have gone faster. Sorry, slower. I would have cruised up all the time. Paul.
So question, go back 2 slides, not thanks. Paul Hoffman. Why did you skip over change the transport since most of the things there work on v6?
Why did I skip over?
Because you said, oh, we'll never have a v6. By the way, I don't want a v6 only world. Let me just say that up front. I'm old enough where I probably will be able to live during a world where there's still v4. But you said, oh, we'll never get a v6 world. But under change the transport, all of those things work just fine on v6.
All of those things
ignore the first bullet. The really changed transports, TLS, Quick, HTTP2, and such like that. Those seem to work on v6. Google might even agree with me on this.
Making DNS more difficult, putting in state for a session, adding overheads, works fine if the thing you're doing generates revenue out there in real world. When it's a piece of beggar bloatware that you invest as little as possible and work on the trailing edge of technologies and still deliver me queries back from the 1970s, changing it to put in an expensive new protocol that demands more hardware, more software, more attention, more money,
and more state,
is kind of anti-gravity.
Okay.
And this is why it's kind of a realistic assessment of you can build it, but will people pay for it and deploy and pay that deployment cost? Which is why I'm kind of writing it off going, I really think we've got to change the transport if we think about v6, but I really think the world is addicted to a free DNS and you're in the tyranny of free, and that's not a very good place to be.
Great, thank you.
Hi, Ray Ballis, ISC. On the question of DNS over TCP, talking about firewalls blocking that, I proposed an experiment that when I was way back doing the stuff on DNS proxies in 5625, the problem with those middle boxes was not that they were blocking TCP, but they simply didn't listen on port 53 TCP. So I wonder whether we could do an experiment with using temporal analysis to tell between an immediate connection refused and the typical delay that you'd get when a firewall is blocking that port.
You know, this is a 2013 experiment and could well be benefit being done again. And oddly enough, using glueless delegation and using code that you wrote originally and playing with it a bit, it's actually relatively easy to set up. Here's the name server of the glue record. Whoops, I've just truncated that.
Yeah.
Go figure out. We could test it, but as to why, whether it's the server is unresponsive, there is nothing associated, actually you could test it. Because most of you are still running some kind of Linux that bleats reset every time I send a TCP packet to an unopened port. God knows why you run that kind of crap, but you do. You shouldn't respond with a reset, but that's a different talk. A reset is normally if I make it to you and you're not listening. A firewall, thank you, simply goes chop, and it's a silent chop. And I'm pretty sure you can measure the difference.
Yeah, I mean, there's quite a difference between
reset
I would
and a
hope
chop.
Being able to say, well, this has been administratively disabled and could in theory be fixed, or simply this isn't listening.
It's an important experiment because, as I said, if you think UDP is going to work in V6, you're on rocks. It just ain't going to work.
Thanks.
Thank you.
Thank you very much. Next, we have Mr. Ralph Weber from Nominum talking about what's in the cache.
There you go. Doesn't it work? Okay, great. So, short introduction. I'm sort of getting old. My beard's getting grayer, and but I've been working delivering DNS services to end users for most of my professional life. So I'm actually did recursive resolvers for a bunch of telecoms in Europe, and now work with Nominum, who does software for lots of telco doing DNS recursive. And other than doing good software, we also offer, well, policy-enabled stuff, which some people like, some people don't. But to do that, especially in the security area, we need data, and we have lots of our customers around the world actually sharing data with us that we look into. And that's, on one part, is DNS query data, and more recently, we also added, more recently is 2 years ago or so, we added a feature to our engines to emit the statistical data that they have. I mean, how many queries I'm getting, how many I'm sending to authorities, and all this stuff. And we emit this every 5 seconds. I mean, because that's still, compared to the DNS query stream, it's not a lot. And this data includes QPS and cache hit rate. So I was wondering, well, all the data we have, what cache hit rate do we actually have? And this is all the data we have. It's a couple of 100 million, actually, data points from hundreds of servers. And the y-axis is the cache hit rate, and the x-axis is the number of queries we are getting, or the numbers of queries these servers are answering. And it's a logarithmic scaled, because, I mean, you'll see most of my slides have logarithmic scales, because we are looking into big data, and when you want to compare the small bits to the big bits, that's the best way to do stuff. So all of this, what in the circle is 0.021% of traffic. So if you are doing less than 1,000 QPS, sorry, you're not a real server out there. I mean, we're not considering you just doesn't make a difference. So we are looking into the big guys, because these days, I mean, especially when you go in the mobile world, I mean, people with their handsets, they are not going to change DNS servers easily. I mean, there are some apps out there, but most of them query their ISP's DNS or their provider's DNS. And when you zoom into that, you'll see if you do more than 1,000 queries, your cache hit rate is above 90%. And if you are doing more than 40,000 queries, which is this thing on the right, your cache hit rate is about 95%. And that's overall queries, including attacks, including every shit that everybody sends you. I mean, 95% gets answered out of the cache. And yeah, that's a summarizer of what I've just talked. And now this was kind of statistical data. Now I want to look into actual query data. So to start with that, I'm going to explain a term we are using frequently. It's called core domain. It's pretty much whatever gets delegated from the registry to the domain owner. I mean, mostly it's a second level domain. There are some like co.uk where it's deeper. There are some where it's deeper and not deeper. So we take care of all this, and we base it on the Mozilla public suffix list, which I think probably a lot of other people are also using for this stuff. And then we can see, okay, on the domain boundaries, what are actually people querying and what are organizations doing? I mean, we have organizations that have more than one domain, of course, but still, we wanted to see the top core domains that we are looking. On the data set, we'll get above 1 million queries per second DNS data from all of our customers around the world. Over the day, it's roughly 100 billion queries. That translates into 7 million core domains. So these are the actual domains, domain owners that are used for it. And as I said, it will be a lot of logarithmic scales. A lot of our customers already have V6. So not all, but a lot. So the A to quad A ratio in the data is about 2/3 A, 1/3 quad A. And with that, that's the distribution. So this is the core domain. The most popular core domain is actually responsible for 8% of the traffic, and then it goes down. If you do some analysis, you get that the top 100 core domains do 67% of all DNS traffic. And the top 1,000 core domains do 90% of all DNS traffic. So you want to look at these guys if you want to have an impact on doing stuff with DNS. Now, this is a top 10 list, I think. As you see, mostly the cache hit rates are absurdly good, with a few exceptions. Now, 6 million core domains in the stuff and the data we analyzed actually have less than 10 queries per day. So these are probably I mean, I would say malware or some stuff that just queries the bot once a day and then it gets done with it, or new stuff. So let's look at the overall cache hit rate distribution. Again, logarithmic scale. So you see on the beginning, it's mostly on the top, and then it sort of boils down with the cache hit rate. And then on the right, what you see, these nice looking things, that's actually when we have, say, 10 queries per day, the cache hit rate only can have 10 different values. And if you go down to, well, 2 queries a day, it can have 2 different values. So that's what you're seeing in this long, long tail there. I mean, everything that's on beyond the really dark stuff is something, well, probably bad stuff. So let's zoom into that. So on the top 100, you see most of them are above 90. We have actually nothing under 65 or so, or 60. So the top 100 are pretty well behaved overall. Now, let's look into the stuff that is maybe not so well behaved. So that's the kind of out of the top 100, the ones that are, well, maybe not so good. You see Akamai, Microsoft, Windows, Dyn, some of that stuff. Those have cache hit rates that are lower than what we normally see, because most of the popular set have very good cache hit rates. And when you calculate all of the cache hit rates over all domains, the overall cache hit rate is 91%. So, I mean, this is something we see on real servers out on the internet delivering service to customers. So let's look at what a percentage, or what of this is actually DNSSEC, or what is capable of DNSSEC. So I took all the 7 million core domains and looked what was actually, I mean, what had a SOA record with a signature. That's what the test I did. And then for that domain, I looked at the cache hit rate. And you see the picture is not as dense as the other one, and it also seems to at least in the long tail, coming to lower cache hit rate. The beginning still probably is as good as the non-DNSSEC. Actually, it might be better. And another thing that you see, the really, really long tail doesn't exist. So that means looks like people who are doing DNSSEC are not doing malicious things, but that's just a guess. You can't really diverge the other data, but there's nothing in the really, really long tail. So overall, it was not much DNSSEC domains, and I should have put the 0.08% of the domains are actually DNSSEC. So what people are, I mean, we might have more DNSSEC domains out there that are actually signed, but that is what are people actually asking from customers around the world, and it's really not that much. And the total traffic that could be validated, which has a core domain of DNSSEC and is 2.5%. Now, we've introduced sort of as a problem for people validating, because if they break something, as all the stuff from the root to the DLD is signed, so if you break something in DNSSEC, we'll have no resolution. But if we are using DNSSEC, we only can really protect us on 2.5% of that stuff. But the cache hit rate is good, and some of their, of the domain popular, vkcache.com, I think, is hosted by Cloudflare, and they are doing a good job getting more people on DNSSEC, and Cloudflare also is up there with popular domains. So we probably need to do more there. So let's look at IPv6, because one of the things that were the motivations, one of the things that were the motivations for this talk was there's work in DNS op at the moment, getting DNS, changing the protocol to answer more than just one thing, maybe A and quad A together, because people might have not getting the answer out of cache. So let's look into where that is. So that's the core domain distribution, A to quad A. So it looks fairly similar. So the domains that are have A records and the amount of traffic they are making is similar to the ones that are making quad A. So let's look into the cache hit rate. That's the blue picture we had earlier overlaid with a purple picture of data points. It looks like, just from looking at it, that the cache hit rate is a bit lower. But again, the most important thing you want to look at are the people up front. So how are they behaving? So let's zoom in there. And there we see actually that it's true, because a lot of the stuff that have 90x cache hit rates now go down to 40 or something, or even lower. So there could be that this assumption that we are having a worse cache hit rate with quad A than I could be right. So let's look a bit deeper in the data. So these are the core domains, the top guys. So it looks like for popular stuff like Apple or, Akka DNS is, I think, the most prominent example where the cache hit rate sort of tails off a hell of a lot. And they are doing lots of data, so we'll look into that. Microsoft is similar. They're also, the cache hit rate on V6 or quad A records is a lot worse than on A records. So we actually then digged out the worst offenders in the sort of top 100, and the cache hit rates, and live.com, I think, is also Microsoft. It's really, really bad. So maybe there is something to do with increasing the cache hit rate, or to do something with the protocol. Overall, it's not that bad. If you compare the top 100, the average cache hit rate is 97 with 8, 91 with quad A, and for the top 1,000, it's 91 to 87. So let's look into data deeper, if the stuff really expires first, or if they don't answer out of the cache. So when I did this, so the base data that I have has usually the client name and the DNS flags, but it doesn't have the answer data. So I had to look into the answer data, and to do that easily, I just give me some of the names I have there, and then do digs. So the DNS OARC. So on the left hand, we see normal queries for A. We didn't do DNSSEC here, so just because that, the dig output would be too big.
So normal query, v6 and v4, both get an answer, all is good. Both have the same TTL, so, I mean, if people have dual stack, that shouldn't be a problem. Let's look how it is when there's no quad A exist, because not all domains have already kind of have v6 servers. So we see on the left-hand side 300 seconds TTL. On the right-hand side, the minimum, which is the negative caching, also is 300, so 5 minutes. So everything good. So why are we seeing this huge discrepancies from A to quad A? So just a reminder on RFC 2308. So negative caching works. The authoritative server sends back in the authority section the SOAR record, and the minimum TTL is the amount of time you have to cache it. And then you put in your cache as a negative record, and you expire the TTL, and then if the TTL expires, you go it off. So, okay, that was working at extended. So let's look at AKDNS, which was one of the domains that had huge problems. So on the left hand, we see sort of the proper answer with A. On the right-hand side, we see the answer with quad A. There's something missing there. There's no authority section, no SOAR record. What do we have to do with this? So RFC 23 has an answer. Negative responses without SOAR record should not be cached. So guess what? We are not caching this, which of course means then next time somebody asks the question, we have to go out again and keep in mind we're answering something that doesn't exist anyway, but we have to go out for it again. And to make stuff more entertaining, there were some domains where I then couldn't quantify the problem. So I looked into these, and this is what live.com is answering. And this really is bizarre, because on the left-hand side, A record, normal stuff. Right-hand side, they don't have quad A. They give an authority section. Great. But the minimum TTL is 0 seconds. What the heck should I do with this? I mean, I have to drop it. There's no way. There's nothing else I can do with it. I have to drop it. So it's clearly bad behavior. Why are you guys doing this? Because you are saying something is not there, and it will not be there for the next 5 minutes, 10 minutes, whatever your TTL is, or the TTL from the proper records. I mean, if somebody turns up v6, is it really that important that it needs to be there the next second? I mean, I don't understand it. And because of this data, I mean, the data that I had to look is now the data that is sent from the recursive to the authoritative, and it's very hard. I mean, people who have written recursive resolver, I mean, correlate the one with the other is really hard because there's such a lot of stuff that can go on that will make you do an authoritative lookup for this, and then, as Jeff said, you have to do a side lookup and this, so it's really hard to correlate. So I had to look into the data to the authorities without actually correlating it to the actual queries I see. So that's just a reminder. And then I wanted to see what the impact was. So I've decided on a couple of things I want to check. So how many A queries, how many quad A queries, how many of these are no answer, no error? And that means, I mean, no answer, no error proper, which with a proper TTL, a TTL greater than 0, and both for v6 and v4. And how many of these are actually non-cacheable, meaning that either they don't have an authority section or they have an authority section with a 0 TTL. So here's what I have. I mean, apple.com would have a bit lower cache hit rate, but not too bad. It looks like that on the v6 they have more negative answers, which if the TTLs are different might explain that a bit. AKDNS really is astounding because 95% of all the traffic there is v6 traffic. And 97% of that is not cacheable. I mean, we could probably could spare a CPU from a caching server if we just wouldn't have to send this. And Microsoft.com is the same. I mean, they have sort of more V6 traffic, and I don't think that they have actually more V6 traffic to the end users. I mean, they just have more DNS V6 traffic, and lots of it is not cacheable. And live.com, while they don't have more V6 traffic, so they actually have a lot of V4 traffic, the non-cacheable number is really, really big. I mean, some of the others I really couldn't figure out what it is beyond looking a lot deeper in the data. I mean, McAfee probably, they're doing the stuff that all the security vendors do. They signal something over the wire. So again, that must not be cacheable, but it also, of course, means that a lot of stuff out there is going through. So, but I think that if you discount all of this from the sort of real V6 traffic, your cache hit rates with V6 will be probably just as good as with V4. So, conclusion, caching works. I mean, and there's nothing better than having a hot cache. And I mean, you have to have a server that does a seasonal amount of QPS, but if you do that, it just works. And I mean, me as an engineer, I'd rather like to work on problems that affect 80–90% of the people than of problems that affect maybe less than 10% of the people. And doing multiple responses, I think, affects not a lot of people. So maybe we should work on actually deploying the standards we have, like negative caching. I mean, it would be great if people would do that. Or empty non-terminals. I mean, that's another thing that's been out there. I mean, there was this talk before. I mean, who said that you cannot really deploy NX domain, there's nothing underneath it, despite a lot of people have in their software. But you just can't turn it on because stuff will break. Because empty non-terminals have been, I mean, a thing that we know how to work to do, but we're sort of ignoring it. And DNS 0 is the same thing. I mean, the amount of code we have in servers to cope with servers that can't do DNS 0 is amazing, astonishingly. Why do we still need to do that? I mean, really, we, rather than working on new features and new stuff, we should actually try to deploy the stuff we have. So, and with that, questions.
Stefan Lagerholm, T-Mobile. I think in terms of the SOA with Zero, every now and then we see on operation mailing list somebody's telling everybody to flush their cache because they screwed something up, right? And I had a talk in Amsterdam a couple of years ago. The recursive resolver, they don't really follow what you tell them in terms of TTL. So if you set the TTL to 15 minutes or 1 hour for the negative caching, it might be, you know, they might not follow that, right? So I think for safety reason, you put it to 0 to make sure you don't cache anything negative, because if you screw up a record and you put something in there you're not supposed to do, then you can easily flush it out. So
yeah, but if
I used to work for Microsoft, so I know that's for a couple of domains.
But if the recursors don't, I mean, our stuff, I think, follows that, so we don't cache it. That's why we see this absurdly high thing. So, I mean, why are you doing this? I mean,
well, because if we put something in there that we weren't supposed to put in, right, we want to make sure that we can remove it as soon as possible.
5 minutes, 60 seconds, is that
bad?
But
if you put 60 seconds in there, it's not gonna work because nobody's following it. Right?
So the thing, if you put in 0, nobody's following it. They put it 50 minutes or something like that. I know that there's software out there that does that. But you put 0 in, the guys who follow and ask again. The guys who don't follow don't give a shit. If you put 60 in, the guys who follow the RFCs will have at least sometimes they cached it. Mm-hmm. And I mean, 60 seconds really, is it a big deal?
If they were to follow the 60 seconds, that would be fine, I think.
I mean, they don't follow if you put 0 in, so it's not, at least that's my experience.
Hi there, Brian Summers from OpenDNS. I found this, one of the first few slides was very interesting, that you said that unless your resolver is doing 40,000 queries or more, the cache hit rates are less relevant.
No, not 40,000. I mean, it was above 1,000 QPS, right. You get cache hit rates above 90%. And if you do, I mean, of course, our servers are a bit biased, so we do software for the big telcos and ISPs, and the lower QPS servers are usually lab servers or test servers, so that's why they are not making up a huge amount of traffic here.
Right. So I'm kind of interested in this, and I will kind of measure our side of things again because it confuses me. So our resolvers kind of do anywhere from, say, 1,000 queries per second to 50,000 queries per second each.
Yeah.
And it's basically the cache rate ratios are the same, more or less, on all of them. So I always kind of explain this by the fact that there are, the kind of top 1,000 domains are the things that get hit most, and everybody's hitting them. And if you take a subsection of people and compare them with another 100 subsections of people, they're all looking up the same stuff, but the outliers are all just random different stuff. And I always explain the ratios being more or less the same with that. But seeing as you're seeing something completely different, I find that one of us probably has to be wrong.
No,
it's probably me.
I mean, it could be that, I mean, as this was a diverse set of servers from everything but Africa and Antarctica. So, I mean, it's from North America, South America, Asia, Europe, and Australia. So it was a diverse set, and I would think that maybe some of the different cache hit rates might be the local stuff, because it always is a function of the query, the traffic that you get, and something like a sort of a DE domain or something like that, it might have a different experience than a .au domain, something like that. But another thing that could be a reason for that is your software doing prefetching?
Yes.
Okay, so that was okay. So
we're cutting the line.
Well, we'll take
Thank you.
offline. Yeah.
Okay, so please make it quickly.
Oh, yeah. Tail at Akamai.com, I just wanted to acknowledge, thank you, actually, because when Ralph told me about this yesterday, it was the first that we heard of this. It is
Yeah, I mean, I discovered it last week when I was looking the stuff for the talks.
Right. It's certainly not intentional behavior, and we will be putting a fix into our next software release that we can get out.
Thanks.
So, yeah.
Robert Evans, Fastly. Could you go back to, I think it was slide 25 with 2308 reasoning? It says should not. It doesn't say must not. Have you considered carefully understanding the implications?
Yeah, it might be a consideration.
Thank you for the work. Whenever you find something crappy like this, please open a pull request for the DNS violations project, so it's at least documented somewhere and somebody else don't need to find the same thing again, and we can at least publicly shame the violators. Thank you.
Okay, I'll find you on that later. Okay, thanks.
Thank you very much, Ralph. We're finishing the testing and measurement track. We're going to have some very important announcements before the break. So, Keith.
Okay. One thing that I would like to do is OARC works with many volunteers helping. We have all our speakers of the program committee. We have various people helping with the webcast. And we also make demands of our board members. We've had a lot of board members over the years. All of them have made a significant contribution, and we like to recognize that. So the person I would like to thank for their service on the board this time is Paul Ebersman. So Paul, if you'd like to come up. I'd like to present you this with our thanks for all your So we're going to break for half an hour. Please fill in the surveys. We don't seem to be getting a lot of survey response, so we would really like to know what you think about the talks. Jerry will be doing the demos at the back there if you'd like to see what he's doing with the software tools. So we can resume. We've still got quite a lot to get through between now and the middle of the afternoon. So if you could all resume promptly at 11:30, that'd be great. Thanks.